Okay, why don't we go ahead and get started? Hello everyone and welcome back to Physics 3150. We're going to start the last topic of this course, which is about the implementation of logic gates using transistors. So up to now we have been going, we've had a bottom-up approach in the second half of the course. We started with basic logic gates such as AND gates and OR gates, inverters, NAND, NOR, XOR, and all that. And then we moved on and built different kind of logical expressions using Carnot maps. And then from there, we moved on to sequential logic design, and we said that we can actually build these little blocks that we call them flip-flops that had a clock in them and enable and reset and all that. So using all these basic logic gates, we could make flip-flops, and using these flip-flops, I could make different kind of sequential circuits such as counters and state machines and state diagrams. So by combination of all of these things, I could make, so this was sequential logic. And then I could, by combining all of these, I could do state machines where I had combinational logic blocks and sequential logic blocks, and I could actually make, I could implement any kind of an algorithm, let it be a combinational algorithm or a sequential algorithm. I could actually implement it using my logic gates and using hardware basically. But since the beginning of the second part of the course, I've been promising that, well, these gates that I've been telling you that these gates are not really the basic blocks that we have. These are also some blocks that could be actually made, that are made using other components that we're going to call them transistors. So as I promised, we're going to talk about the internal circuit of our basic blocks, right? So basically we went from we had a bottom-up approach, but then now we're going back to the basics. We're going back to these AND gates and NAND gates and NOR gates, and we're going to look into how to implement these things using transistors, because we said that all of the amazing things that are happening because of integrated circuits, because of electronic circuits, are because of these little devices that we call them transistors, and everything is built using them. So first we need to know, well, how do we build these basic logic gates, and then if we know how to do that, then we can actually build anything that is more complicated than that, because all of the state machines and sequential logic and the flip-flops and anything else that we have discussed in this course are made using these AND gates and OR gates and inverters and other basic logic gates. So let's get started with that discussion as the last topic of this course. So in our designs, we're going to be using two different kind of transistors, and we use transistors as switches in this course. So we're going to use MOSFET transistors. So MOSFET stands for metal oxide semiconductor field effect transistor. Okay, so we're going to use N-type MOS, or sometimes we call it NMOS, most of the times actually, or P-type MOS, or PMOS. Okay, in terms of symbols, both of these, like basically NMOS and PMOS, they're both 3-terminal devices, and they both have, well, they're actually 4-terminal devices. We're not going to talk about the 4th terminal in this course because it's not going to be used much. So we're just going to talk about the 3 terminals. So basically they have gate, drain, and source. And for PMOS, we have the exact same symbol, but then it has a little bubble at the gate. So it's the same order, so gate, drain, source. So we have a bubble showing that it's kind of like inverted version of NMOS. We have seen in this course that wherever we have a bubble, it's kind of representing the inverted kind of behavior. Both NMOS and PMOS are symmetric devices, meaning that I could have called this source and this drain, or this source and this drain. So the important thing is that the one that is actually the terminal that is here or here is always gate, but then the other two could be source or drain. Okay. Now, the NMOS or the MOSFET could operate in different regions. So in terms of operating regions, we could have an off state, and then we could have saturation and triode or linear. So this is the most useful region. Saturation region is the most useful region of operation for MOSFETs if we are using MOSFETs in analog circuits and if you want to use them as amplifiers. So the best, well, not the best, because best might imply that the other regions might actually be useful. It's actually the useful region in analog amplifiers. So we didn't discuss in this course, we didn't discuss about the internal circuit of an op-amp, but if we do, it's built using transistors, and the transistors in an op-amp are all working in the saturation region, and the operation of an NMOS or PMOS, a MOSFET, a transistor in the saturation region, is entirely different from its operation in the triode region. Okay, so we're not going to talk about this region. If you're more interested in this, you can take the course ECS 2210, Introduction to Electronic Circuits and Devices. Over there, you can actually learn more about MOSFET amplifiers and the use of MOSFETs as an amplifier in analog circuits. How about the other two? Well, these two regions are used, or they're useful in digital circuits, which is the topic of this course. So why is it very useful? Why these two regions? Basically, if we are off, basically using these two regions, we can see that the transistor becomes a simple switch, meaning that it is either conducting current or not conducting current, and that's what we need in digital. We need a device that has a 0 state or a 1 state. It connects 2 points or it doesn't, right? So basically, we're going to be, so in digital circuits, we will use transistors as switches. Okay. Now, just to give you a simple idea, again, if you want to know more about this, you can take this ECS 2210 course, or even like more advanced courses on semiconductor devices. But generally, the idea of a transistor is quite simple, at least from the zero order. So basically, imagine you have a piece of semiconductor like silicon, and if I look at the cross section of the silicon, looking into this surface and magnify it here, basically what you can do is that the way that we make transistors basically is that we put a piece of insulator. Okay, so normally this insulator is silicon dioxide, so SiO2, and then on top of that we put a conductor layer. It used to be metal, now it's something called polysilicon, but the important thing is that it's a highly conductive material. So let's call that metal for now. And here we had our silicon, right? And then silicon is a type of material. The special thing about silicon is that it is a semiconductor material. What does that mean? Again, it takes 10 minutes for me to actually explain to you what is the special thing about semiconductor material compared to a conductor or an insulator. But then you can imagine that it's a kind of a material that you can tweak it or manipulate it to become a conductor, or like basically you can actually manipulate its conductivity by a large range. So you can make it almost completely an isolator or completely a conductor, right? So that's the nice thing about silicon, and that's why semiconductors have changed our lives. And then that's why that part of California that all these electronic companies are there is called Silicon Valley. Anyway, if you take a silicon substrate and we put this insulator, so let's call this insulator here, and then a metal on top of that, and then using a process called diffusion, we grow to conductive sections inside the silicon. So this is basically conducting. Okay. If you must know, it's basically a highly doped silicon, n-type silicon. So basically it's a semiconductor that has been made a very conductive material. Okay, so if I have this thing, like if I have this structure and then I connect my terminals to it, let's say I connect drain here and source there, I could have had it the other way around, and this is always gate, then the first thing you notice is that I have basically a metal here, and then an insulator, and then a semiconductor as the silicon. So it's kind of like a sandwich of metal, oxide, semiconductor. So that's where the MOS is really coming from. So basically, because metal is a conductor and silicon is, well, a pseudoconductor, and in between I have an insulator, it is almost like I have a capacitor here, right? Because a capacitor is a conductive plate, an insulator in between, and then another conductive plate. So I'm connecting this to my gate, and then the body of the silicon is, let's say, connected to ground. By the way, this body is the fourth terminal that I was talking about. So sometimes in the symbol, they show something like this and they call it body or substrate. Okay, so that's the terminal, the fourth terminal that we're not going to be talking about, because most of the time for NMOS transistors, it is connected to ground, and for the PMOS transistors, it is connected to VDD. Anyway, back to our discussion. So we have a capacitor here. So the whole idea of a MOSFET is that initially there is no conduction, there's no current going from source to drain here, right? Why? Because there's simply a normal silicon doesn't have enough free electrons to support this current. But then if I apply enough voltage at the gate, so if V gate goes up and it goes past a certain threshold, as I increase the voltage at the gate, it means that I'm actually increasing more and more charges on the top plate of the capacitor that absorbs more and more charges to the bottom plate of the capacitor. So I'm going to have more and more free electrons absorbed and brought up, basically absorbed from this region and from this region, and at some point I'm going to have so much free electrons in this region that it makes a channel for my source to drain, my S terminal and D terminal. Basically, I'm going to have enough electrons, enough free electrons here that I can actually have conduction between these two, and I kind of like short the source to drain this way, right? So if I actually, there's a very nice basically path for electrons to start from source and go all the way to drain. And that's why we actually call them these names. So source is really sourcing the charge carriers, and drain is really, well, draining them. And gate is really, you can think about it as a gatekeeper. So it basically, the voltage on the gate tells us that if we do have a channel down here or we don't, right? So by increasing and decreasing this gate voltage, we can open and close this channel. And that's the whole idea of a transistor, at least from a digital perspective. So again, if I want to show it based on the symbol, if this is your transistor, basically this is your gate, the gatekeeper, and then we have drain and source. And the electrons, because the electrons are going from source to drain, the current is actually always drawn from drain to source. But that's the direction of the current, at least for digital circuits, is not that important. The important thing is that we have gate, drain, and source. And if the gate voltage goes up, and passes a certain level that we call it threshold voltage, I'm gonna have conduction between drain and source. If it goes down and below the threshold voltage, I'm not gonna have this current. Okay. So now what's the difference between NMOS and PMOS? Well, the main difference is that the type of material that I use. So for NMOS, I'm using N-type silicon, and for PMOS, I'm using P-type silicon. The difference that it makes is that for PMOS, I have to actually make the gate voltage smaller than a certain voltage to actually activate the channel. For NMOS, I have to make it larger than a certain voltage. So generally, for NMOS, we want to connect the gate to VDD when we want the channel to be there. For PMOS, we want to connect it to ground if we want the channel to be there. We're going to discuss a lot more about this. So if this is too much information and you got a little bit confused, don't worry. We're going to talk a lot more about these two devices. Okay. I talked a lot about the structure of a MOSFET and why is it called MOSFET. By the way, the FET part, the field effect transistor, is really coming from the fact that because the whole channel creation and basically the generation and degeneration is really coming from the effect of a field. You have more positive charges at the top plate of the cap, that causes more, that brings up more negative charges to the channel and creates the channel. But anyway, we talked about a lot about the MOSFET and why is it called MOSFET and how is it actually built. But for the sake of this course, this is all you need to actually know. So we have an NMOS that looks like this. I'm going to draw it like this so that you know that you can turn this symbol as much as you want. So we have gate, let's call here drain and source. Could have been source and drain. And the principle of operation of an NMOS is very, very simple. If gate is 1, also known as VDD, so if I connect the gate to supply voltage or VDD, therefore source and drain are connected, so source is connected to drain. If gate is 0, also known as, well, 0 or ground, therefore S is not connected to drain, right? So source and drain are disconnected. Based on this, you can actually guess how the PMOS is going to be operating. So I'm going to have the same terminals, gate, source, and drain. And then if gate is 0, this time source and drain are actually connected. If gate is 1, source and drain are not connected. Okay? So it's as simple as that. So for the rest of this lecture, I'm going to cover two different topics. First, I'm going to talk about, we're going to analyze circuits. So we're going to build transistor-based circuits and try to analyze their behaviors and try to figure out what kind of a logic they're actually trying to implement. Then the next part of this lecture, I'm going to be talking about the reverse of that process. Basically, how to design certain logic expression using transistors. For example, if you're told to design an AND gate, how would you actually design it? Well, for basic logic gates such as AND and NAND and NOR, we kind of know their structure after a few examples, but then if you've been given a sum of product, let's say you have solved your Carnot map and you have reached to a sum of product terms, how do you actually implement that using transistors? Okay, so that would be the next part of our discussion. So first, let's talk about circuit analysis, and let's start with the simplest possible circuit that we can have. So let's say that I have this PMOS transistor and this NMOS transistor, and I've connected, to be more exact, I've connected the PMOS transistor on one end to VDD, and the NMOS transistor is connected to ground, and the drain of NMOS and drain of PMOS are connected to each other. The gates of the two transistors are also connected to each other. I'm going to call that input, and the drains that are connected to each other, I'm going to call that output. Okay, so just to remind you, this is gate, source, drain, source. Okay, so you might actually ask, why this is source and this is drain, and why not vice versa? As I said, it's a symmetric device, so you don't really need to actually worry too much about that. Okay, it's really coming from me knowing what is the direction of current in this circuit, and then trying to actually name these things in a way that the current always basically flows in a way that the charge carriers are always moving from source to drain. That's as much as you should care about it. But anyway, even if you don't know what is which one is source and which one is drain, we can still analyze the circuit as much. The only thing we need to know is that which one is gate, and I think gate is always obvious, is the clear one. Okay, now if somebody asks you that what would be the truth table, if you want to draw the truth table of this circuit, meaning that, well, it's a one input one output circuit, so if the input is 0 or 1, what would be the output? How do you go about this circuit? This is one of those times that I ask you guys to actually pause the video, try to actually figure out what would be the output for the two cases, and then resume the video, and we're going to solve it together. Okay, I hope that all of you have tried it. Let's do it together. So let's start talking about input being 0. If input is 0, well, that 0 is connected to the gate of both NMOS and PMOS. So let's analyze them one by one. If input of an NMOS is 0, I look it up here and I see that the NMOS is going to act like an open switch, right? So basically, my output is going to be, so if I want to redraw the circuit, basically, at least on the output side, I'm going to have an open switch here to ground. How about on the PMOS side? On the PMOS side, I see that when gate is actually equal to 0, source and drain are actually connected to each other. So on the PMOS side, I have a closed switch, and that goes to VDD. Therefore, and this is my Vout. Therefore, I can easily say that my Vout is equal to VDD, which is a 1. Now, if I do the same analysis when input is 1, you will see that the NMOS switch is actually on, and the NMOS switch is actually closed, and the PMOS switch is open. Therefore, the output is going to be 0. Okay. Looking at the truth table, we can see that we just built our first gate. It's the inverter. So this is the internal circuit of an inverter that had an input and an out, a single input and a single output. And using two transistors, I could actually make this inverter very simple and easy. Okay, so basically, the main idea here is that we have to analyze these transistors as simple switches. Okay, now we're going to talk about a lot of other gates, a lot of other circuits. But one thing that you're going to see that is common among all of these circuits is that they always have two sections. There's always a pull-up network and there's always a pull-down network. What do I mean by that? I mean that there's always a VDD up here, some circuitry, and some other circuitry, and basically ground. We call the midpoint Vout, and the inputs are connected to actually both of these. So I could have, in this case, I only had one input, so input number 1, but I could have multiple inputs here. So I could have input 2 all the way to input N. Okay, so there's always a pull up network and a pull down network. Why do we need that? Because we know that from all of our logic circuits that we have been discussing, the output, I shouldn't have called it Vout, I should have just called it output. The output is always either 0 or 1, right? It can't have any other value. So when it is 0, it means that it is connected to ground. So there should be a certain circuit that whenever we need the output to be 0, it connects the output to ground. And there should be another kind of a circuit that whenever we need the output to be 1, it connects the output to VDD. We call the VDD connection circuit pull up network, and then we call the ground connection circuit pull down network. Okay, so in this case, our pull up network was simply a transistor, and pull down network was also, so this was all pull up network, and this is our pull down network. Okay, and they're both simple transistors. Okay, we're going to see more complicated circuits, and you're going to understand, hopefully understand this concept a lot better. Okay, let's look at another example. Let's say that this is my VDD. I have, this time I'm going to have two inputs. So let's say I have a PMOS here, another PMOS in parallel with that. And the two PMOSes are coming here, they're connected to each other. And then I have two NMOSes that are actually in series with each other, going to ground. Okay, I'm going to connect one of the NMOSes to input A. I'm going to connect the same input to here. So here's also A. And the other one, I'm going to go with input B. And I'm going to connect this B to the other PMOS as well. Okay, so just to make this a lot cleaner, I'm going to basically just write A and write B here so that you know these are the same signals are connected to the input of both NMOS and PMOS. This makes the circuit much cleaner and easier to analyze. And as I mentioned before, I'm going to call the output, the midpoint, the output. Okay, and now the question is, what is the logic that this circuit is actually representing? So I'm going to have A and B, and the truth table is going to have 4 rows. 0, 0, 0, 1, 1, 0, 1, 1. So the question is, what would be the output for each of these cases? Again, this is one of those times that I want you guys to pause the video, try to solve it, and then we'll do it together. Okay, so let's actually solve this together. So first, 0, 0. If I have 0, 0, well, before actually analyzing the circuit one by one, let's actually try to see if we can get any intuition in about this circuit. I can see that I have two transistors in series with each other from output to ground, right? And I know that output becomes 0 only if both of these transistors are conducting, right? That's the only way that the output could be connected to ground. So it's kind of like an AND operation between A and B. We might we might be actually motivated to say this is an AND gate, but then we have to wait. So let's see if A and B are both 1, because an NMOS transistor requires the gate to be 1 to be conducting. So I want both, let's call this M1, M2, M3, M4. Okay, so M1 and M2 should be conducting for me to get an output equal to 0. So if I want M1 and M2 to be conducting, A and B should be both 1. If that happens, I'm going to get an output that is 0. Okay. There is one little thing that you have to also consider, that are we sure that at the same time that how we are sure that at the same time that my NMOSs are conducting, my PMOSs are not conducting? Because what will happen if I have a VDD shorted to the output and also a ground shorted to the output? What would be the output? Is it a 0 or a 1? Well, this is a situation that we never want to happen. And then in the circuits that I'm going to provide to you, this will never happen. We're not going to have any situation that the VDD and ground are racing to set the output or to force themselves to the output. There's always either VDD or ground is connected to the output, and never both of them. Okay. And then we're going to look into, when we start talking about the design part of this lecture, we're going to see that how do we design the circuit. That's another goal that we should have, how to design these transistor circuits so that this situation never happens, that we never connect the output to both VDD and ground. It's always one of them. Okay, so now we know that output is connected to ground if we have 1 1, and if I look at the PMOSs, just to make sure, just as a sanity check, I know that when A and B are both 1, both of the PMOS switches are open, therefore my output is not connected to VDD, so I'm happy. Okay. Any other situation, I know that if A is 0 or B is 0 or both of them are 0, I know that definitely my output is not going to be connected to ground, because I need both of them to be 1. So it better be connected to VDD, right? The other situation, the other forbidden situation that I don't want to have is to have 2 open switches to VDD and ground. Nothing is actually driving my output. That's also something that I don't want. So these are things that I don't want. Okay, so let's look at what happens. So if I get one of the A and B to be 0 or both of them to be 0, I can see that because I have a parallel structure up here at the PMOS side in the pull-up network, I can see that either of them or both of them being 0, both of inputs, I mean, being 0, they connect the output to the VDD. Therefore, I'm going to have output being 1. Okay, so I can say that for the other 3 cases, I'm going to have a 1. So what is this gate? Well, we know this gate as something is called NAND, or this symbol that we had before. Okay, so this is how you actually make a NAND gate. Okay, so just as a review or as a reminder, the yellow box is really your pull-up network, and the orange box is your pull-down network. Okay, let's move on. Let's look at another example. Let's say that if I do the exact opposite of this, meaning that the PMOSs are actually in series and the NMOSs are in parallel. And again, the midpoint, I'm going to call it output. And the inputs are pretty much the same thing. So I have A and B here and here, A and B here and here. Okay. And by the way, you saw in this circuit that it didn't really matter if A is up here and B is like A is connected to M1 and B to M2, or vice versa, or the same thing about M3 and M4. And that is the reason that it really doesn't matter if I have connected A to the one input of the NAND and B to the other, or vice versa. These circuits are kind of like working independent of the order of the inputs. Okay, so the same thing here. So for the second circuit that I have here, doesn't matter which one is A, which one is B. The important thing is I draw it like the structure of the transistor is the important thing. Okay. Now, what would be the answer to truth table, or like what is this gate? Again, pause the video, try to do it yourself, and then we'll do it together. Okay, I hope you've done this yourself. Let's try to think about this. So again, if you think about it, the output only connects to the VDD if both A and B, if both, let's call these transistors the same names. So M1, M2, M3, M4. If both M3 and M4 are conducting. So when do two PMOSes, or basically when do PMOSes conduct? When their input or the gate terminal is connected to 0. So I need A and B to be 0 to have an output that is 1. So I'm going to get a 1 only if and only if both of my inputs are 0. Now, for the rest of the cases, I have either one of the inputs equal to 1 or both of them equal to 1. That is enough for me to have one of the two NMOSes, M1 and M2, conducting, meaning that output is going to be connected to ground, meaning that my output is going to be 0. So looking at this, you can tell that this is a NOR gate, and the symbol that we had for it, just as a reminder, is this. Okay, so this is an A, this is B, and this is the output. Okay, let's talk about the next example. This time, we still have a 4 transistor circuit. So 2 PMOSes in series and 2 NMOSes in parallel. But this time, instead of A and B, I'm going to be connecting A bar and B bar as the inputs. And again, same as before, output is the middle point. So the question is, I'll do the truth table and figure out what kind of a gate this circuit is representing for different values of A and B. Again, pause the video, try to do it yourself, and then we're going to do it together. Okay? So hopefully all of you have done this and have got some results. Let's discuss this together. So let's talk about the first row. A and B both are 0. If A is 0 and B is 0, therefore A bar is 1 and B bar is 1, meaning that both of these NMOSes, let's call them M1, M2, M3, M4, M1 and M2 are going to be conducting, therefore output is connected to ground, therefore output is going to be 0. Again, if A is, so this tells me that either of A or B are 0, M1 or M2 or M2 are going to be conducting, therefore I'm going to get an output that is connected to ground, therefore my output is going to be 0. So for the second and the third case, because A is 0 in the second and B is 0 in the third case respectively, I'm going to get 0 and 0. If A and B are both 1, then A bar and B bar are going to be both 0. Therefore, both of these PMOSes, M3 and M4, are going to be conducting. Therefore, my output is going to be 1. Okay, so this is a very well-known gate. We know that this is an AND gate, and the symbol is like this. Okay, now you might think that, okay, so this is an AND gate, but then I know that an AND is really a NAND plus an inverter, right? And I know how to build those circuits. I know that a NAND, how to build a NAND, and I know how to build an inverter. So for a NAND, if I want to draw it quickly, we had something like this. And this was A, B, A, B. So if this is an AND gate, and this was connected to ground, if I connect the output of the NAND gate to the inverter, which looked like this. So I had just a PMOS and an NMOS, and they were connected together. And if I connect the output of the NAND gate to the input of the inverter, I can call the output of the inverter out, and this is also an AND gate, right? So now the question is, well, now I know how to build two AND gates, and it's a good time to actually make some comparison and then think about, by the way, these are the same VDDs. I know that it's probably obvious to you, but it doesn't hurt to say that. Okay, so this is the same VDD and these are the same grounds. Now, the question is, which one of these designs is better? Right? Which one of them? And it is one of them that is better, and that's how we actually make an AND gate. It's basically one of them that we always use to make an AND gate. Okay, it's not the obvious answer, so I would encourage you to actually pause the video, try to think about it, and then come back and resume the video, and then try to see if you guessed it right. Okay. So the idea is really coming from the number of transistors used. The answer is basically the number of transistors. So here, for the circuit on the right, I have 4 transistors for the NAND and 2 transistors for an inverter. So I have 6 transistors, right? How about the circuit on the left? Well, it looks like 4 transistors. And that's why I said it's not clear, or it's not the obvious choice. But if you think about it, my inputs are actually A bar and B bar, but I care about A and B. I'm not going to be connecting A bar and B bar to an AND gate. I'm going to be connecting A and B to an AND gate. So what I'm really not showing and trying to basically hide it here is that each of the A and B needs to be inverted before actually be connected to this circuit. And for each inverter, I'm going to need 2 transistors. So this circuit is really 4 transistors that we see, plus 2 transistors for inverting A, and 2 transistors for inverting B. So I'm going to have 8 transistors. So this is actually, the circuit on the right is actually the better way of implementing an AND gate. Okay, so this is why back when we were talking about simple logic design, I was telling you guys that normally we built everything based on NAND, and then I know that we defined the NAND gate as an AND plus an inverter, but in reality you can see that an AND is really a NAND plus an inverter. Okay, this is one of those counterintuitive things that happens in the digital logic design. Okay, so now that we have learned how to analyze circuits, transistor-based circuits, and you're going to see more and more examples of this in the assignment, but the main idea is very simple, and it's basically very similar to what we have done already up to now, that you just basically draw the truth table and then consider every different combination of the inputs and then figure out if the output is going to be connected to VDD or ground. It's as simple as that. Now let's talk about the reverse process. Let's say that an expression, for example, f is equal to x1 bar ANDed with x2 plus x3. Let's say this Boolean expression is actually given to us. So if this is given to us and it's a 3-input expression, it's not really in the form of a sum of product, but we have a Boolean expression and somebody tells us that we want to implement a custom design transistor-based circuit that implements this logic. Of course, I can say that this is going to be basically an OR gate, and the result is going to be ANDed with this x1, and then, well, it's actually x1 bar. So first I need to invert x1 and then AND that with the OR result of x2 and x3, and it should be done. And I know how to make AND gate, an OR gate, an inverter, so I can easily actually implement this logic. So for an OR gate, I know that it's a NOR plus an inverter, similar to an AND gate. So it's going to have 6 transistors. So an OR gate is going to have 6 transistors. And then inverter for the x1 bar is going to have 2 transistors. And then the AND between x1 and x1 bar and x2 plus x3 is going to cost me another 6 transistors. So we're really talking about 14 transistors, right? The other thing that is important here is that we're really talking about 3 levels of operation, meaning that first I need to calculate this x1 bar, and then I have to calculate the x2 plus x3, the OR of these two, and then the results are actually ready. Or actually, I can do the first and second together. So first, I need to actually calculate x1 bar, and at the same time, I can calculate the x2 plus x3. And then once the results are ready, I can actually go ahead and AND them together. Okay. If you think about it, the AND and OR are two-step logic levels. So meaning that first you need to calculate NAND, then invert that. So we're really talking about a two-step thing, and then one step here in parallel. So two steps in total. And then we have to do the AND, which is another two step. So we're talking about 4 different steps or 4 different layers. Okay. So of course I can do this, but can I do better than that? Can I implement this with less than 14 transistors and 4 layers? Because each layer, if you think about it, if each of these gates have a nanosecond of delay to actually provide you with the output, if I have 4 layers, I'm going to have 4 nanoseconds delay. And you might think, oh, 4 nanoseconds is not that long of a time, but then think about millions of transistors and millions of these gates, and then you will realize that you care about every single nanosecond. You realize that if maybe this 14 transistor, given that each transistor is going to take a few nanometers, doesn't seem much. But then again, if you think about billions of transistors, then you will realize that, well, we're talking about a percentage of, and knowing that most of our blocks are made using these basic blocks, you will realize that we're talking about a huge fraction of our circuit that could be actually reduced, and we could have a much more compact design. Okay, so the idea is that how to design the transistor-based circuits when a expression like this is actually given to us. To do that, first we need to actually make a couple of observations. We have to look back and see and look at the circuits that we have seen up to now, because those are standard CMOS circuits, and I'm going to tell you why we call them CMOS. Okay, so we're going to be talking about standard CMOS design. So up to now we have talked about NMOS and PMOS. CMOS is really standing for complementary MOS. What do we mean by complementary? If you remember, I talked about this pull up and pull down networks, right? So one of them pulling the output down to ground, and one of them is pulling up the output to VDD, and the inputs are connected to both of them. So the idea is that, remember, there were 2 forbidden states for these pull down and pull up. The first forbidden state was when VDD was connected to the pull-up network, and the pull-up network was actually active, and the pull-down network was also active. So the output was connected to both input and output, both VDD and ground. That was something that we never wanted to happen, because we can't say with certainty that if the output is going to be a 1 or a 0. We want the output to always be connected to either of VDD or ground. So the other forbidden state was when we have both pull up and pull down network disabled. So meaning that the output is not connected to neither VDD or nor ground. So that's also something that we never want. We want the output to be always connected to something that is known, so that we can tell if the output is a 1 or a VDD, not an unknown kind of a state. Okay, so to make sure of this, we have to make sure that the pull up and pull down network are complement of each other. Meaning that whenever one of them is conducting, the other one is not, and whenever is, well, and vice versa, right? How did we make sure of that? Well, we did 2 things at all times when we were designing. There are many ways to actually implement different logic expressions using MOSFETs, using NMOSs and PMOSs, but this is the standard CMOS way. So there were 2 observations. One, pull-up network was all PMOS, and pull-down network was all NMOS. So this didn't really help much in terms of being complementary. It was mainly because PMOSs are generally better at connecting things to VDD, and NMOSs are better at connecting things to ground. The reason for that, again, really comes from the physics of transistors, and I have to actually explain to you a little bit about the relationship between the gate source voltage and the threshold voltage. It's beyond the scope of this course. Just remember that one of the rules for CMOS, standard CMOS design, is that in the pull-up network you should only have PMOS transistors, and in the pull-down network you should only have NMOS transistors. Okay. Number two, the structures are complementary. The structures are complementary. What do we mean by that? I mean, if you look at for example, the NAND gate, oops, we had two parallel PMOSs and two series NMOSs. So whenever I had series NMOS, I had parallel PMOS. Whenever I had parallel NMOS, I had series PMOS. The example for that was NOR. So with the NOR gate, I had series PMOS and parallel NMOS. Okay. And for inverter, I have just basically one transistor on each side, so there's no meaning for complementary. So number two rule is that if I have two transistors in the pull-down network that are in series, they're going to be in parallel when I go to the pull-up network. And if I have vice versa, well, it's going to be the opposite. Okay. And then there is a rule number three, which is not really a rule. It's more of an observation that we can actually make by looking at the circuits that we have had up to now. If you look at it, you will see that, well, from the beginning of the second part of this course, when we start talking about digital logic design, we saw kind of that, like, basically a series combination of two things, like for example, two NMOS transistors. A series combination kind of implies ANDing, right? And parallel implied OR, right? Whenever we, like, if you remember when we started the digital logic part of this course, we were talking about switches turning on light bulbs, right? And over there, when we had two switches in series, that was kind of like implying an AND. And when I had two switches in parallel, like this, it was kind of implying an OR gate, right? Now, the observation that I want to make is that if you look at all the circuits that we have talked about up to now, you will see that the pull-down network is the knot of whatever we want to, is kind of like basically implying the knot of what we are trying to implement. What do I mean by that? So for example, for a NAND operation or a NAND gate, the expression that we're trying to implement is AB bar, right? That's the Boolean expression for a NAND gate. Knot of that would be AB. If you look at the pull-down network of an AND gate, pull-down network, it looks like this, which is kind of implying an AND operation, which is AB. So it's the knot of what we wanted to have. We wanted to have AB bar, knot of that would be AB, and that is what the pull-down network, so let me complete this circuit, pull-down network of an NAND gate is really representing, right? The same thing with a NOR gate. So for a NOR gate, we're really talking about A plus B bar, right? Knot of that would be just A plus B, and pull down network of a NOR gate, you can see it here, that it's just basically two parallel transistors. Okay, so it looks like that I can use these three rules to implement any circuit, any expression that I want. First, I need to figure out what is the knot of that circuit, of that expression. Once I have the knot of that expression, then I'm going to basically implement the NMOS part, because I know that the pull-down network is going to be basically, if I know that the knot of the expression is A plus B, I'm just going to put two transistors in parallel. If I have AB, I'm going to put two transistors in series, right? Then, once I have the pull-down network, I can use rule number 2 and say, well, because the two NMOSs are in parallel in the pull-down network, the PMOSs must be in series in the pull-up network because they have to be complementary of each other. And ta-da, I have my circuit. So I kind of use rule number 3 first, and then went to, so in terms of like basically order, I start with rule number 3, then go to rule number 2, and I kind of have rule number 1 in mind that, well, pull-up network is all PMOSs and pull-down network are all NMOSs. So that's how we actually design standard CMOS circuits that will never result in these two situations, the forbidden situations, and basically we don't have to actually go and use the standard gates to actually make things, because we can do custom design for the expression. Most likely we're going to get to better implementation in terms of the number of transistors and layers. We're going to solve this example in the next slide, and we're going to see that how this is done. The same expression that we have here, we're going to actually solve it using this step-by-step approach and see if we can do better than 14 transistors and 4 layers. Okay, so the function that I had that I wanted to implement was f equal to x1 bar and with x2 plus x3. So if you remember, for example, for a NAND, we said that our function is really a v bar. Therefore, we saw f bar is equal to ab. And then this is a series NMOSs in pull-down network. And that's how we build, PDN in pull-down network. And that's how we built an AND gate. Okay. Now, this means that first I have to do f bar. So f bar is going to be x1 bar. Sorry, this was x3, not x3 bar, x2 plus x3 bar, right? Now, looking at this, it's not as simple as AB. So it's not, from the first look of it, it's not as simple as AB to be implemented. And we didn't expect something easy from this example. But what I can say is that if I call this x2 plus x3, because I know that x2 and x3 should be, it seems that they are actually in parallel, right? Because there's a plus between them. And then they're in series with the x1 bar. So if I call this z, I can write this as x1 bar z bar, right? So in a sense, I can say that I know I'm going to have x2, or maybe I have to draw it up down here so that I can draw the pull-up network later. So I know that I have x2 and x3 as two switches, two NMOS switches in parallel going to ground. And the combination of the two is going to be in series with something that I'm going to call x1 bar, right? And that's my pull-down network. But wait, this is not my F. It's actually, there's something that we shouldn't forget, and that's the big bar up here, right? When we were doing F bar for NAND gate, we didn't have the big bar on top of the AB. That's why I didn't need to do anything extra. So we're going to get to there, but then first let's do the pull-up network. So for the pull-up network so I know that the output is going to be at the midpoint. However, for the pull-up network, I'm going to say the transistor, let's name them, M1, M2, and M3. The transistor that was connected to X1 bar, M3, was in series with the other two, with the combination of the parallel combination of the other two, right? So now it should be in parallel with the series combination of the other two. So in the pull-up network, I should have one transistor in parallel with series combination of the other two transistors. So that transistor that is in parallel now is still X1 bar, and those two transistors are X2 and X3. The order of X2 and X3 doesn't really matter in the pull up or pull down because they're in series or parallel. And that's it. I go to VDD. So again, the transistor, the M3 was in series with the parallel combination of M1 and M2. Therefore, the let's call it M4, M5, and M6. So M3 was in series with the parallel combination of M1 and M2. Therefore, M4 is in parallel with the series combination of M5 and M6. Now, this out is really representing F bar because of this big bar up here. So what do? I actually have to connect this to an inverter. And that is my F. So this is really F bar that we have created here. So the difference between this example and the NAND gate was that for the NAND gate, the F bar didn't have, the F bar was simply AB. So I basically made AB by making two NMOSes in series with each other, and then completed the circuit by building the complementary circuit at the pull-up network. But for this one, for this example that we're just solving right now, the F bar has a big bar on top of it that we have to address it, right? So the first thing we did was we kind of built whatever is under the bar, and then we inverted the result. Okay, so now let's analyze this and compare it to what we had before. What we had before was 14 transistors and 4 layers. Here I have, well, 1, 2, 3, 4, 5, 6 plus 2, 6 transistors plus 2 transistors. And then don't forget that X1 bar needs another 2 transistors. So this is for X1 bar to create it from X1, right? So we're really talking about 10 transistors. And how many layers? Well, the first step, I need to actually calculate X1 bar before actually running this step, right? So there's a step here that I'm going from X1 to X1 bar. And then once I have X1 bar, I have all my inputs. Then I do the middle stage of my circuit. And then that will give me F bar. And then once F bar is ready, I can actually go from F bar to F, right? So this is X1 to X1 bar. This is X1 bar, X2, and X3 to F bar, and this is F bar to F. Therefore, I'm going to have 3 layers. So this is an improvement to what we had before, which was 14 transistors and 3 layers, but you can see that it's not perfect because I still have this third layer, which I just have to, it's kind of like looks very inefficient because I have to generate an output and then flip it. And the question is, can I generate the output directly? Can I use a method to generate the output directly? Okay, this is our third try to actually solve the design question that we had. We had this expression F is equal to X1 bar, X2 plus X3, and we wanted to actually implement this using transistors. So in the last try, we saw that the problem was F bar had a big bar on top of it. Whenever we have that, we have to invert the output. So we're going to use 2 things this time. One is we're going to use the fact that X bar is actually equal to X. This is one of the rules of the Boolean algebra. And the second rule is really coming from De Morgan's law. So the fact that XY bar is equal to X bar plus Y bar, or X plus Y bar is equal to X bar Y bar. Okay, so I'm going to use these, and I'm going to say, instead of looking at F bar, I'm going to look at F bar bar, because that's equal to F, and that's equal to X1 bar, X2 plus X3 bar bar. Now, the nice thing about this is that I can actually move forward and break one of these bars down and keep the other one up there, because if I keep it up there, it's kind of like, well, we're going to talk about it. So first, let's break it down. So I'm going to say that this means that I'm going to keep the top bar up here, break the second bar using De Morgan's law. I'm going to say this is going to be x1 bar bar plus x2 plus x3 bar. Okay, so I used this, the second rule that I have there, or the first version of De Morgan's law. Now this is equal to x1 plus x2 plus x3 bar, and then a bar on top of everything. Okay, so if this is the expression that I'm dealing with, then you can say that the f bar of this expression is really x1 plus x2 plus x3 bar, right? And then from here I can see clearly that this is a parallel combination of the transistor that is connected to x1 and this thing here. And what is that thing there? Well, I can further break this down, but then if you look at it, it's simply a NOR gate. It's one of those basic gates that cannot get any simpler than a 4 transistor. So I don't have any motivation to do that, right? So what I would do is that I can actually look at it from this f bar point of view, or I could have actually seen this and said that if, again, x2 and x3, it's kind of like basically I have x2 NOR with x3, and then the result is NOR with x1. So I can implement this as simply going with, so because this is x2 and x3 NOR with each other, this is the x2, x3 NOR with each other. We know this circuit from before. And I know that the result is going to be, again, NOR with x1. So I'm going to have a very similar circuit here. Let's call this x1. And this is, for now, I'm going to keep it as is. And the two PMOSs, again, this is x1. And then I say the output of x2 and x3 NOR together should be connected to the input of this circuit. Okay? So this is really, at this point, I have x2 plus x3 bar. And at the output of this, I'm going to have my function output. So now, with this design, I'm going to have 8 transistors. And the more important thing is that it's only a 2-layer. I don't need to invert anything at the input or output. So we got from a 14 transistor, 4-layer design all the way to 8 transistor, 2-layer, almost 50% saving in terms of transistors and in terms of the speed of our design. Okay, so we're going to see a lot of more. So this is the way that normally we design transistor-based circuits. We always put 2 bars on top of them, break one of them, keep the other one, so that we can actually design them using those 3 rules that we've seen before. You're going to see more examples in the assignments after the after the submission is due. I'm going to actually post the solutions. You're always welcome to email me, book an appointment during the office hours, and ask your questions about the assignment or any other questions that you have about the course. This was the last lecture of this course, so I hope that you guys enjoyed the material and you feel that you've learned something in this course. Good luck and have a great summer.